The workshop in Tula smelled of cutting oil and freshly machined steel. Winter light came through windows that had seen decades of Russian winters, illuminating particles of metal dust suspended in the cold air. On the workbench sat a rifle that looked simultaneously familiar and foreign. The wooden stock followed traditional lines, but above the barrel ran a tube that had no place on the Mosin Nagant rifles that millions of Soviet personnel carried. Fedor Vasilyevich Tokarev stood before that table in early 1940, not with triumph, but with the calculated awareness of an engineer who understood that perfection was a luxury and function was a demand. The rifle before him was his second attempt at solving a problem that had already consumed years of his life. The SVT-40, his previous design, had taught him what worked and what failed when theory met field operators, mud and maintenance schedules stretched past breaking. This newer iteration, already being called the SVT-40, incorporated every lesson written in reports from the field. The barrel was shorter by several centimeters. The cleaning procedure had been simplified. The metalwork had been reinforced at stress points where the 38 model had shown cracks, but the essential logic remained. Capture the energy from firing and use it to perform the work a user's hand would otherwise do. Next to the rifle lay a cross-sectioned barrel, a teaching tool that revealed what normally remained hidden. The gas port drilled through the barrel's top surface was barely 5 millimeters in diameter, yet through that small aperture would flow the entire operating principle of the equipment. Tokarev had calculated the port size with precision. Too large, and the system would be violent, battering parts and accelerating wear. Too small, and the rifle might not cycle reliably with varying ammunition or fouling. The short-stroke gas piston system represented Tokarev's answer to competing demands. Soviet doctrine needed volume of fire. Soviet logistics needed simplicity. Soviet manufacturing needed designs that didn't require exotic materials or impossibly tight tolerances. And those in the field needed something that would function when maintenance was delayed and conditions were hostile. The gas system had to self-compensate, had to be adjustable, had to acknowledge that entropy was part of every equation. Around Tokarev, the Tula arms plant operated with the perpetual urgency that marked Soviet industrial facilities in that era. Past regional conflicts had demonstrated new realities about infantry engagement. Reports from observers watching tensions across Europe added confirmation. The establishment understood that doctrine and equipment needed to evolve together, and they had given Tokarev the resources and pressure to make it happen. He picked up the rifle, feeling the weight distribution. The magazine well accepted the 10-round detachable box cleanly. The bolt cycled smoothly through its rotation, the locking lugs engaging with precision. The trigger mechanism, redesigned from the SVT-38, had a cleaner break. Every refinement was documented, measured, justified. Engineering was not art. It was decision-making under constraint, and Tokarev had spent his career learning which constraints mattered most. On the wall behind him hung technical drawings that represented months of calculation and revision. Gas pressure curves, metallurgical specifications, dimensional tolerances. Each line on those drawings translated into machining operations, quality control checks, and ultimately, performance in the field. The distance between what worked on paper and what worked in a person's hands was where engineering either succeeded or taught painful lessons. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Tokarev's path to that workshop had been neither direct nor accidental. Born in 1871, he had lived through the transformation of struggle from single-shot rifles to rapid-fire systems, from horse cavalry to mechanized columns. By 1940, he was 69 years old, but his mind remained engaged with problems that younger engineers struggled to solve. Age had given him perspective about which innovations mattered and which were distractions. The Soviet military's interest in semi-automatic rifles predated Tokarev's involvement. Throughout the 1920s and 1930s, various designers had submitted proposals, each attempting to balance firepower with reliability. Some designs used complex mechanisms that worked beautifully in pristine conditions and failed significantly when exposed to dust or cold. Others were so simple they were essentially manual actions with gas systems attached, offering minimal advantage over bolt-action rifles. Tokarev approached the problem with a philosophy shaped by decades of design. He had created the TT-30 and TT-33 sidearms, which became standard. Those tools taught him about what operators could maintain and what they couldn't. A tool that required specialist-level skill for basic cleaning was one that would fail in service. Complexity was expensive, not just in manufacturing, but in sustaining performance across time and conditions. The pressure in 1938, when he finalized the SVT-38, had been intense. The Red Army wanted modernization. Leadership wanted demonstration of Soviet technical capability. But the truest pressure came from physical reality. Could you make a rifle that automatically chambered the next round, using nothing but the energy already present in the firing event, and have it work reliably for a person who might have minimal training and even less time for maintenance? The SVT-38 had proven the concept, but revealed implementation weaknesses. The rifle was too long for practical use in vehicles or confined spaces. The muzzle brake, while reducing recoil, was prone to damage. The stock design, while traditional, didn't adequately protect the gas system from impact. Cleaning procedures required more disassembly than field conditions could reasonably accommodate. Each of these issues appeared in reports with the clarity that only operational use provides. Tokarev took those reports seriously. Unlike designers who viewed criticism as an attack, he treated it as data. Every complaint about the SVT-38 became a requirement for the SVT-40. Shorten the barrel, strengthen the stock, simplify the disassembly, revise the muzzle device, make the cleaning procedure something an operator could perform with cold hands in fading light. Behind these technical decisions lay a broader understanding of how large organizations function. The Mosin Nagant rifle was robust, simple, and familiar to millions. Any replacement had to offer clear advantages while not requiring complete retraining of maintenance infrastructure. The SVT-40 needed to be enough better to justify its complexity, but not so complex that it became a liability rather than an asset. Tokarev also understood manufacturing realities. Each SVT-40 required approximately 3 times the machining hours of a Mosin Nagant. It used more steel. It required more skilled labor. In peaceful times, these costs might be acceptable. But Tokarev was designing in 1939 to 1940. As international tensions rose and Soviet industry prepared for demands that would eventually become desperate. The rifle had to be manufacturable at scale, not just as a prototype or limited run. The gas system itself represented careful compromise. Gas-operated mechanisms had existed since the late 19th century, but making them reliable required understanding the relationship between gas port size, piston mass, spring rates, and bolt carrier velocity. Too much energy and parts broke. Too little and the action wouldn't complete. The system had to work across a range of ammunition, factory fresh loads, aged supplies or materials found in the field, and across environmental conditions from summer heat to winter cold that could freeze lubricants and make steel brittle. The operating principle of the SVT-40 could be described in a sentence, but understanding why it worked required examining each component's role in the energy transfer chain. When the firing pin struck the primer, it initiated a chemical reaction that converted solid propellant into expanding gas. That gas accelerated the projectile down the barrel while simultaneously creating pressure that wanted to push everything backward, the casing, the bolt, the entire rifle. In a bolt-action rifle, the operator manually unlocked and cycled the bolt, providing the energy to extract the spent case and chamber a fresh round. In the SVT-40, Tokarev designed the rifle to do that work itself by borrowing energy from the firing event. The key was the gas port drilled into the barrel approximately 20 centimeters from the chamber. At that point, the projectile had already accelerated to high velocity, and pressure in the barrel had peaked and begun to drop, but remained substantial. Gas flowing through that port entered a cylinder positioned above the barrel. Inside the cylinder sat the short-stroke piston, a hardened steel component roughly the length of a thumb. The gas struck the piston face, driving it backward against its own inertia and friction. The piston traveled only about 15 millimeters before striking the operating rod, transferring its momentum. Then the gas pressure dropped and the piston stopped, its work complete. This short-stroke design was Tokarev's critical choice. The piston didn't travel with the bolt carrier, didn't add reciprocating mass to the full operating cycle. The operating rod, now driven backward by the piston's impact, pressed against the bolt carrier. The bolt carrier was a substantial component that rode on rails machined into the receiver. As it moved rearward, cam surfaces on the carrier engaged with cam surfaces on the bolt itself, rotating the bolt and unlocking its locking lugs from the barrel extension. Only when the bolt was fully rotated and unlocked did the carrier pull it rearward. This sequence mattered. The bolt could not unlock while chamber pressure remained high, or the casing might rupture. The camming system ensured mechanical disadvantage during initial movement, slow rotation, strong leverage, followed by rapid rearward extraction once unlocking was complete. The extractor claw gripped the rim of the spent casing, pulling it from the chamber. An ejector pin struck the case head, pivoting the case out through the ejection port. As the bolt carrier reached the rear of its travel, it compressed the return spring and prepared the internal mechanism for the next shot. The entire system was now loaded with potential energy. The compressed spring and the carrier held at the rear of its stroke. When the cycle continued, the spring drove the carrier forward with force sufficient to overcome friction and strip a new cartridge from the magazine. The bolt face pushed the cartridge into the chamber. The cam surfaces rotated the bolt, locking the lugs into the barrel extension. The rifle was ready to be used again. Each component in this chain had to be precisely engineered. The bolt lugs had to be strong enough to contain chamber pressure, but able to rotate smoothly under the camming forces. The extractor had to grip firmly, but release cleanly during ejection. The return spring had to provide enough force to ensure reliable feeding, but not so much that it accelerated the bolt carrier violently. The magazine spring had to present cartridges at the correct angle and with sufficient force, even when the magazine was full and spring compression was maximum. Tokarev's genius lay not in inventing these principles. Gas operation and rotating bolts already existed, but in implementing them with appropriate simplicity. The SVT-40 had no small screws that could vibrate loose, no tiny pins that could be lost during field maintenance, no springs so delicate that rough handling would deform them. Every part was sized to be manufacturable with 1940s-era equipment and maintainable by users with basic tools. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The transition from SVT-38 to SVT-40 represented systematic refinement based on operational feedback. Test facilities at Tula ran thousands of cycles through prototype rifles, measuring wear patterns, recording malfunctions, and analyzing failures. But laboratory testing could only reveal so much. The true validation came when rifles entered service and faced conditions that no test program could fully replicate. Field reports from late 1939 provided crucial data. The SVT-38 performed well in trained hands under good conditions. Accuracy was adequate for standard distances. The self-loading mechanism reduced the time between shots, but problems emerged when conditions degraded. In muddy environments, the long barrel and exposed gas system collected debris. In extreme cold, lubricants thickened and the action became sluggish. Those unfamiliar with semi-automatic operation sometimes failed to maintain the rifle properly, leading to stoppages that could have been prevented. Tokarev methodically addressed each issue. The barrel was shortened, a modest change, but one that improved handling in vehicles and close terrain. The muzzle brake design was revised to be more robust and less prone to damage that could affect accuracy. The stock was reinforced where it covered the gas tube, providing better protection against impacts that could misalign the system. The cleaning procedure received particular attention. The SVT-40 required removal of the gas tube and disassembly of the piston assembly for thorough cleaning, a time-consuming process requiring multiple tools. The SVT-40's gas system could be accessed more easily. The piston could be removed without removing the entire gas tube. A person could perform field maintenance with just the tools carried in the rifle's stock compartment. Testing also revealed the importance of the gas regulator. Under ideal conditions, with fresh ammunition and a clean bore, the rifle cycled reliably with the regulator set to its minimum position. But ammunition quality varied. Propellant formulations differed between factories and production runs. As the bore accumulated fouling, gas pressure at the port decreased. The regulator allowed compensation for these variables without requiring springs or parts replacement. The adjustable regulator had 3 positions, accessed by rotating a collar near the gas block. Position 1 allowed minimal gas flow, suitable for high-pressure ammunition or clean conditions. Position 2 was the normal setting. Position 3 opened the gas port to maximum, used with weak ammunition or when the rifle was heavily fouled. This adjustability acknowledged that real-world operations didn't maintain laboratory conditions. One might fire thousands of rounds with minimal cleaning. Ammunition might come from stocks that had aged in less than ideal storage. The rifle needed to function across this entire spectrum. Durability testing pushed rifles beyond normal service life. Some test equipment functioned for tens of thousands of cycles to identify wear patterns and failure modes. The short-stroke gas system proved advantageous here. Because the piston didn't travel the full length of the action, wear was concentrated in a smaller area and could be managed through material selection and heat treatment. The operating rod, bolt, and carrier showed predictable wear patterns that could be monitored and addressed during professional maintenance. Tokarev also considered human factors. The safety selector was positioned for easy access, but designed to be positive, difficult to accidentally disengage. The magazine release was tool-free, but required deliberate pressure, preventing accidental drops. The bolt hold-open engaged after the last round, providing a clear indication that the magazine was empty. These details might seem minor individually, but collectively they represented the difference between a design that worked on paper and one that worked in a person's hands. By the time the SVT-40 received final approval for mass production, it incorporated hundreds of small refinements over its predecessor. None of these changes revolutionized the design, but each one reduced the gap between theoretical performance and field reality. Engineering rarely advances through revolutionary leaps. More often, it progresses through careful attention to why things fail and methodical elimination of those failure modes. Among all the components in the SVT-40, the gas regulator embodied Tokarev's deepest understanding of how equipment actually functions in service. This small adjustable collar, positioned just forward of the chamber where the gas tube began, represented an admission that perfection was impossible and adaptation was essential. In design terms, it was a compromise. In practical terms, it was wisdom. The regulator worked through simplicity. Inside the gas block, the port drilled through the barrel could be partially covered by rotating the collar. In position 1, the collar blocked the most gas flow, allowing only minimum volume to reach the piston. In position 3, the collar was fully open, allowing maximum gas to enter the system. Position 2 fell between these extremes. An operator could adjust it without tools, simply by rotating the collar until it clicked into the desired position. Why did this matter? Because every assumption made during design eventually encountered reality's variation. Ammunition specifications provided a range of acceptable charges, not a single perfect value. That range meant that different cartridges might generate slightly different gas pressures. Multiply this across multiple factories, production runs, and storage conditions, and the variation increased. The regulator allowed the rifle to function across this entire envelope of possibilities. Consider the effect of barrel fouling. Each use left residue, burned powder, and metallic material inside the bore. Over long periods without cleaning, this residue accumulated, particularly near the gas port. The accumulation effectively reduced the port's diameter, decreasing gas flow to the piston. A fixed gas system might begin to malfunction as fouling increased, failures to extract or chamber properly. The adjustable regulator allowed compensation. As the rifle became fouled, the operator could open the regulator to position 2, then position 3, maintaining reliable function even as gas pressure at the port decreased. Temperature also affected operation. In cold weather, propellant burned less efficiently, generating lower pressures. Lubricants thickened, increasing friction in the action. The combination could cause a rifle tuned for moderate conditions to fail in winter. Opening the regulator allowed more gas into the system, providing additional force to overcome the friction and ensure the action completed its cycle. Conversely, in hot conditions with fresh ammunition, closing the regulator prevented excessive battering of parts, extending service life. Tokarev could have designed a non-adjustable system optimized for average conditions. Many designers made that choice, accepting that performance would degrade at the extremes of the operating envelope. But Tokarev understood logistics and operational reality. Ammunition would vary, maintenance would be delayed, rifles would be used in conditions ranging from Siberian winter to Central Asian summer. The regulator provided resilience across that entire range. The positioning of the regulator also mattered. Placed near the gas port, it was accessible without major disassembly, but not so exposed that it could be accidentally adjusted. The three-position design provided enough adjustment range without overwhelming the user with complexity. The clicks provided tactile feedback, allowing adjustment even with gloved hands in poor light. Every detail served function. In technical documentation, the gas regulator received minimal attention, a single paragraph explaining the three positions and when to use each. But in that small component lived an entire philosophy about engineering for real-world service. Tokarev wasn't designing for ideal conditions. He was designing for mud, cold, fatigue, aging ammunition, and maintenance intervals that might stretch far beyond recommended schedules. The regulator was his acknowledgement that equipment doesn't live in factories or test ranges. It lives where conditions are hostile and perfect is impossible. Modern designers study the SVT-40's gas system because it demonstrated principles that remain relevant. Adjustability provides resilience. Simple mechanisms survive complexity, designed for the worst conditions, not the average. The gas regulator, easily overlooked in discussions of barrel length or cartridge selection, quietly represented some of the most mature engineering thinking in the entire rifle. The SVT-40 entered service in 1940, but its full deployment story became entangled with history's larger movements. When the borders were breached in June 1941, the Red Army faced industrial and logistical challenges that no pre-war planning had fully anticipated. The SVT-40 required more manufacturing time, more skilled labor, and more raw material than bolt-action rifles. As factories moved and production demands became desperate, simplicity gained value that sophistication couldn't match. Approximately 1.6 million SVT-40 rifles were manufactured during the conflict, a significant number, but far fewer than the Mosin-Nagant rifles that continued to serve as the primary equipment. The SVT-40 saw extensive service, particularly with specialized units, marksmen, and personnel who received training to maintain the mechanism properly. Field reports documented both successes and challenges. The rifle provided the promised volume of fire and performed well when maintained. But under extreme conditions with minimal maintenance, simpler designs proved more forgiving. This outcome didn't represent engineering failure. Tokarev had delivered what was requested, a reliable semi-automatic rifle capable of service under field conditions. What the design encountered was a context that exceeded the original requirements. The pressures of a massive struggle prioritized immediate production volume over long-term capability advantages. A rifle that took 3 times longer to manufacture yielded 1 unit, where 3 simpler ones might have been produced. When losses demanded rapid replacement of equipment, that calculation favored simplicity. The SVT-40's influence extended beyond its original service. Opposing forces captured significant quantities and issued them to their own groups, often preferring them over their own standard rifles for the self-loading capability. This cross-adoption was rare. Groups typically viewed captured equipment as curiosities, not primary tools. The fact that they actively sought SVT-40 rifles and that their logistics supported their continued use spoke to the design's fundamental effectiveness. Post-conflict, the lessons from the SVT-40 informed subsequent development. The gas-operated rotating bolt system became standard in regional design. The SKS, adopted in 1945, used a similar operating principle with refinements based on experience. Later, the AK-47 employed gas operation with a long-stroke piston, trading some of Tokarev's precision for even greater simplicity and reliability in the most extreme conditions. Each of these designs carried forward principles that the SVT-40 had validated. In the history of technology, the SVT-40 occupies a specific position, not as the first of its kind, nor as the most produced, but as a demonstration that self-loading infantry tools could function reliably even in demanding conditions. It proved that gas operation, carefully implemented, could survive service that would destroy more fragile mechanisms. It showed that adjustability could provide resilience when conditions varied beyond design specifications. For engineers studying equipment development, the SVT-40 offers lessons that transcend its specific mechanisms, designed for real conditions, not ideal ones. Build in adaptability where perfect consistency is impossible. Accept that complex solutions sometimes lose to simple ones, not because the complex solution fails technically, but because the context includes factors beyond pure performance. Understand that engineering serves operational needs, and operational needs exist within larger strategic and logistical frameworks that engineering cannot control. Tokarev's rifle, designed in 1940 by a man nearly 70 years old, embodied mature thinking about what tools need to do and how they need to do it. The gas regulator, the short-stroke piston, the simplified maintenance. Each choice reflected understanding accumulated across decades of design. The SVT-40 was not revolutionary, but it was profoundly competent, and competence under real-world constraints is often the highest form of engineering success. Today, examples of the SVT-40 rest in museums and collections, their mechanisms still functional despite decades of age. The gas systems still adjust, the bolts still rotate, the springs still return. The rifle that Fedor Tokarev refined in 1940 continues to teach anyone willing to examine how energy becomes motion, how constraints shape decisions, and how engineering serves needs that extend far beyond the workshop where designs begin. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.